Okay, what I'm going to do is derive the moment generating function of a binomial. Well, we know what the answer is because I did it before, but I'm going to do it in a different way. Well, it actually is the same way, but I'm going to do it in a different way anyway. Well, it's the same but different. Okay, so what I'm going to do is I'm going to work out the moment generating function sub x of t, where x is distributed as a Bernoulli with parameter p. So what does that mean? That means that x equals, it's only got two values, it's either 0 or 1. 0 is failure and that's success. So it fails with probability 1 minus p and succeeds with probability p. So it's like tossing a coin or something. Well, there it is. So what's the moment generating function of x as a function of t? Equals the expectation of e to the t x, which equals the sum from n equals 0 to 1, probability that x equals n. Well, you see, I say it's sum from n equals 0 to 1, but look here, it's either 0 or that's like there's only two possibilities. Times e to the tn. So that's all it is. So it's equal to, well, we do the two cases. There's the 0 case, and here's the x equals 1 case. So what's the probability of that? That's 1 minus p, probability of failure, times e to the t times 0. Why is it 0? It's because here, that's n equals 0, yeah? Plus, because it's a sum, of p, e to the t times 1, because n equals 1 in that case. It's a bit of a peculiar case, but there it is. So it's 1 minus p, because e to the 0 is equal to 1, of course, plus p e to the t. So I'll just write that out again as 1 minus p plus p e to the t. Beautiful. Okay, there it is. Now what we're going to do is work out the moment generating function for s of t, where s equals x1 plus x2 plus x3 plus dot 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 plus xn. And each one of these is Bernoulli with probability p, and the xi independent. So what we're doing, because we're adding all these separate ones together, look, there they all are, the zeros don't count for anything. If it fails, that's like a 0. Where are we? That's a fail. And that's success. There it is. So we ignore all the failures and just count up how many successes we've got. And of course, by definition, that's the definition of a binomial distribution. Well, let's have a look at it then. So and we know the moment generating functions of all these. We know that m sub xi of t is 1 minus, it's up here, look, there it is, 1 minus p plus p e to the t. Now we use that fact from Wikipedia. Well, you can prove it if you like, but the moment generating function of s of t equals mx1 of t times mx2 of t times all the way up to m sub x n of t. So the moment generating function of the sum, and here s equals x1 plus x2 plus dot 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 plus xn. Super. Okay, so we're going to get the moment generating function of the sum, which is what we want. This is the moment generating function of the binomial, equals, well, it's just the product. It's just the moment generating function of all the separate ones all multiplied together. So it's 1 minus p plus p e to the t to the power n, because we've got n terms here. So when we write it all out, we just, well, we knew that anyway. Now this is the clever bit. Now you've got the moment generating function of the binomial distribution, at no point did we need to think about getting the probability mass function of the binomial. We just went straight to the moment generating function. Once we'd got the moment generating function of the Bernoulli, which is this one here, we just raised it to the power n to get the moment generating function of the binomial distribution, which is pretty good, really. Pretty good. Okay, I'm going to stop there. Have a good one.